I'm going to make some force diagrams here. So this little system schema thing, we are not going to do that. I'm just going to focus on the force diagrams over here. So this is a typical kind of situation here. I might add those little lines to show that those are equal. Object motionless right there. We use these little subscripts to indicate the nature of the force that we are indicating in the diagram. Okay, so box is sliding to the right at a constant velocity with no friction. So this should remind you of the bowling ball in the no touch zone. And one of the hugest misconceptions, I always use a capital N for my normal forces. That's not the misconception. One of the biggest misconceptions that there is in the world that people have about physics and how things work is that if something's moving, like to the right in this case, that there must be a force in that direction. That is not true. Fake news. It's not true. So you know, because you watch the broom ball stuff, that if there's no friction present, if there's no force in this direction here, slowing the box or impeding let's just say opposite to the direction of motion, then there is no force required or present in the forward direction. And it's not just like it could be this. If these are the conditions, if this is really frictionless and it's sliding to the right at a constant velocity, then this is the force diagram, right? It is exactly this. I think part of the reason that we are so stuck with this, no pun intended, stuck with this misconception is because we live in a very sticky world. There's friction everywhere. There's air resistance. Every surface that comes into contact with some other surface, even if it's like kind of low friction by design or just by nature, there's friction everywhere. And so it feels like to us that there always has to be some forward force or some kind of effort in the direction of motion. But that's because we have an extra friction force here. So it helps sometimes to just think about, well, what would it be like in like deep space, in the absence of any kind of gravitational field or friction or surfaces to like set things down on. If I just gave this pen a push out there in deep space, it would just keep going, right? There's no forward force required for it to do that. And the force, like as soon as I let go of it, it's not like the pen has some kind of memory of me applying a force. That force is gone. All right, so box being pushed to the right and there's no friction. Okay, so there is this applied force, you could call that FP, force of push, or a force A, like applied force, whatever you like. This one, I would like you to call it force of gravity. Those two are equal. This one, I don't know what it is. It doesn't have to be equal to those. Now, question, could that be moving at a constant velocity? Answer, no. It would be accelerating in this direction because, just like with broom ball, when there's extra tapping in that direction, that is unchecked or unbalanced by some other force in the other direction. So it would be accelerating, its velocity would be changing in that direction to the right. All right. Here, we get a box being pushed to the right at a constant velocity. So constant velocity means that the forces are balanced. And I mean, obviously, these forces are vectors, right? They have like magnitude. We draw them like vectors. They have magnitude and direction. So one of the ways you could say that forces are balanced, it's the same as saying the sum of all of the forces is 0. Constant velocity, or if you're at rest, then the forces are balanced too. But constant velocity is a balanced force condition. Okay, so if I've got constant velocity here and friction is present, then in addition to my force of gravity and my normal force, I also have the pushing force and the friction force. And those are equal to each other. So the forces are balanced. This balances this, and this balances this. How about a box being pushed to the right and accelerating to the right, and there's friction present? Well, let's see. If it's accelerating to the right, there must be some extra force in the direction of that acceleration. So that's my normal force, my gravitational force. Here's my applied force, force of push. And there's a friction force here, but I want to make it clearly look smaller, because if we're accelerating to the right, then this is overcoming that, not balancing it and maintaining constant velocity, but overcoming it and causing an acceleration. How about an object that's slowing due to friction? And it looks like I think that's what these little like motion lines mean. No indication that there's a forward force. There's nothing pushing on this. So normal force, gravitational force, and then the force of friction. Wait, is it possible that this thing could be moving in this direction, but the force on it is like this way? Is that possible? Sure it is. It just means it's slowing down. Right? Just like the broom ball at the end of the course, when the ball's coming toward the box, and you saw our teachers who helped me out there, thanks again to them, you saw them tapping opposite to the direction of motion. So the ball was rolling this way, but they're tapping this way to slow it down. So that's very similar to what's going on here. There's box falling, no air resistance present. Well, got no support there. Right? That is called free fall, my friends. Box falling and accelerating downward, and there is air resistance present, but it's accelerating downward. Okay, so that means the down direction is winning, and there's some force. You could call that force of air. Sometimes we call that a drag force, whatever you like. What if a box is falling in the presence of air resistance and the box has reached terminal velocity? What the heck is that? Well, maybe you've heard of that. Did you know that if a person jumps out of an airplane, they don't just keep accelerating, getting faster and faster and faster toward the surface of the Earth. There's a point. The thing about air resistance is, and you know this because probably at some point, whether your parents approved of this or not, you stuck your hand out the window of a car that was moving, well, probably at various different speeds. You've done this. Now, if you're just like pulling out of the parking lot or out of your driveway or whatever, and you got your hand out the window, you can feel the air, right? But if you stick your hand out the window when the car is going 70 miles an hour down the interstate, then you feel a lot more force from the air on your hand. So the faster something is moving through the air, the more force it experiences from the air. So what happens is when a person jumps out of an airplane, for example, they accelerate at the beginning because there's more gravitational force than there is air resistance, because they're not falling downward that fast yet. But as they fall, as their velocity increases, the force of air resistance increases also, until it gets up to the point where they're moving so fast that the air resistance force on them matches the gravitational force on them. And what does that mean? Well, if the forces are balanced, then they start falling at a constant velocity. And of course, if the velocity is constant, then this settles into what it is, which keeps them balanced, which keeps them going at a constant velocity. And we call this the terminal velocity. It's that velocity that causes the amount of air resistance to match the amount of gravitational force. And at that velocity, the person will continue to fall at a constant velocity. So what is that for a person? It's about like 100 to 120 miles an hour. It depends on the shape that you put your body in. So there you go. An object is suspended from the ceiling. Okay, so tension force here. So we're not talking about the forces. We want a force diagram for the box here. So, of course, there's the force of gravity, and then there's a force upward. I'm going to call that a tension force. You could write Ft. Sometimes I just use a T, capital T like that for tension. Like that. Box is not moving. They're balanced. If you're thinking, well, what about the string pulling down on this? Well, sure. You want to make another force diagram for the ceiling? I don't. I'm just making one for the box. So, yeah, the string's pulling down on that, but that's not the object that we're making the force diagram for. An object is suspended from the ceiling. Now there's two strings. So how are you going to do that? Well, there's two different tensions, and they're balancing out this one. So I'm just going to do two right next to each other. I'm going to try my very best to make them both go straight up. Right? So that's, you could call that tension 1 and tension 2. They do have to be, those two have to be equal to each other, and they're going to add up to this. Why those two have to be equal to each other, if they are attached like this, is something that that's for a little bit later in the year. But suffice it to say right now that if one of them was greater than the other, it would cause the block to rotate, and it's not rotating, so they must be equal to each other. All right. And actually, that's not entirely true. If they're, I'm assuming that they're like kind of spaced out evenly, like from the center of it, which actually kind of looks like they're not, doesn't it? So if they're not, if you had one here and then another string here, like those actually would not be equal. But anyway, point for us here, all we need to know is those two tension forces are going to equal that. So there's not really any geometry way. I can't do like tick marks on those because this is bigger, so that's fine. We'll leave it like that. Object is suspended from the ceiling. Tension forces can only act in the direction of the string or wire or cord or whatever it is. And then I have a gravitational force. So if you look at this, you're like, okay, so, I mean, this thing's not moving, so are those balanced? Is there any way we can do a better job of indicating the balance that's happening here? The answer is yes. All the stuff that we did with vectors is going to come in very useful for us here with forces, because I can take this T1 and T2 and break them up into their horizontal and vertical components, like so. And then I can see that these will cancel each other out in the horizontal direction, and in the vertical direction I have this plus this equals that. And there's not really any geometry way of indicating that, but I can see what's happening there. And it's much easier to see once you break these up into horizontal and vertical how things can balance. All right. Box being lifted at a constant velocity, there's no air resistance. If it's being lifted at a constant velocity, that means the forces are balanced. I know that's counterintuitive. It's going up. You want that one to be bigger, don't you? But it's not. If that one was bigger, then it would be going up, but it would be accelerating upward. There would be extra force, an unbalanced force upward. How about box being lifted accelerating upward? All right, there you go. That's what you wanted. So I'm going to exaggerate that. How about the box being lowered at a constant velocity? Oh, you're not going to like this. So the box being lifted at a constant velocity and lowered at a constant velocity, the force diagrams are exactly the same. So if you only have the force diagram, if the only thing you know about the situation is this condition, then you don't know. The only thing that you can say, if you know the forces are balanced on something and you have no other information, you can say, well, that object must be moving at a constant velocity or at rest, and you don't know the direction of that velocity. All right, last few here. How about a box being lowered and it's accelerating downward? So if it's accelerating downward, it means that the down direction is winning. How about a box accelerating down a ramp with no friction present? So we're going to have a lot of practice making force diagrams like this. And this is a very important skill to be able to do this. The first thing that I'm going to do is make a dotted line that represents the direction of this ramp here. Now, when things are on ramps, gravity points off to the side like this. Just kidding. Gravity doesn't care about what we're doing, about boxes and ramps or anything else. It just tugs downward on things. You would be amazed how many force diagrams I have seen over the course of my physics teaching life where students want to put gravity going this way. But of course, that cannot be right. Okay, now after I do that, gravitational force, the support force, this ramp right here, can't support the box in this direction. It's kind of the same as like the tension force here. A normal force can only support perpendicular to the surface. So I actually turn my paper that way so I don't have to kind of, I don't have to stress my artistic abilities trying to draw a perpendicular line to another slanty line. And then how do I see what's really going on here in terms of like balance, what's balanced and what's not balanced? I will tell you right now what we're going to do. So opposite to this normal force, you could imagine that this gravitational force, as if the ramp direction was like an x-axis, and this right through the normal force, perpendicular here, is the y-axis. What if we broke up the gravitational force along those? So I'm going to go down first, and then over. And notice I'm not going down to here and going over like parallel to this line. I'm going down and over parallel to my x-axis, which is the ramp. So I broke the gravitational force up into two directions that are perpendicular to and parallel to the ramp. That might seem at first like a weird thing to do, but this helps us understand exactly what's going on. This part of, this component of the gravitational force is balanced by the normal force. And then this, that's the down the ramp part of gravity. That is what's causing the acceleration. This is the unbalanced part. If I knew this angle, we can do a little, let's see, that would be the force of gravity times the sine of that angle, right? It's opposite to that. So much more with situations like that in your future. How about a box accelerating down a ramp and there's friction present? All right, that looks exactly like this. So I'm going to draw my slanty axes that are lined up with my ramp. Of course, gravity doesn't give a flying banana about what's going on. It's always just straight down. So I can break that up into its components like that. And then there's my support force, which is balancing this. And then if it's accelerating down the ramp, but there is friction. So there is a friction force. The friction force would have to be up the ramp. Friction is always opposite to the direction of motion. But I have to make sure that that it's less than this, because the down the ramp direction is winning. So just make a little baby force of friction in there. All right. And then last, rock climber is wedged in a crevice. Friction with the wall prevents sliding. So there's a gravitational force. And then this is tricky to do because when we talk about free body diagrams or force diagrams, we're essentializing objects down to just a point. In other words, we're not considering all the different parts of the object and forces that might be applied to those parts. We'll do a little bit more of that later in the year. So this is a tricky one because there's really the friction forces on the person are up, and the four of them, I'm not going to try to draw all four. What I'm going to do here to keep things a little simpler is I'm just going to make one sort of consolidated friction force that represents all of those. And then also, the person is pushing on the wall, and the wall is pushing back on the person. So there are forces from the wall because person is pushing on wall. Hey, a force is an interaction between two objects, right? So the person-wall force is just one thing. Wall experiences it in this direction. Person experiences it in this direction. So there's all these normal forces. And again, I'm just going to consolidate the ones to the right, that'd be from this wall, and then the ones to the left from this wall. And I would call those normal forces because they are perpendicular to these surfaces, and those would also be equal. So that's one way of doing that. This would be a situation for later in the year where we wouldn't essentialize the person down to a dot. We would like put the forces like at their point of application. So that's a little tricky, but just to get us to think. All right, there's some force diagrams for you.